In this video, we are going to take some time to talk about what a differential equation is. So this is just a little bit of an intro to what we're going to be looking at for the next few lessons. Uh, Differential equations are any equations that involve the derivative of an unknown function, and the solutions to a differential equation is going to be the function that has the derivative that you begin with. So you start with a derivative and you're trying to produce a function that has that as its derivative. We've kind of solved some of these already. I'll show you where we've done this previously, even though we weren't using the exact same terminology and or notation when we encountered this issue earlier in the year. Now, differential equations is a huge field. I took a class getting my undergraduate degree and then another class getting my master's degree that both were dedicated to solving differential equations. The differential equations we look at are going to depend on first derivatives, so they're called first order, and they're going to be ordinary, meaning they don't depend on what's called a partial derivative. Because of all these other sorts of differential equations and classifications of them, some of you that go into an engineering field in college are going to have to take a course entirely dedicated to solving this. So what we're going to be doing over the next few weeks is just kind of, maybe the first week of that differential equations course that you would take for 15 weeks after you complete your calculus sequence in college. So here is where we've encountered this issue previously. So these problems from our antiderivative chapter earlier in the year, if you look at 39 through 42, directions ask us to find the function satisfying the conditions. So they present us with a derivative and they tell us that the function value at 0 has to be 4. So I worked out number 39 here, but what I did when I worked it out is I worked it out with the notation more similar to what we're going to have to be doing throughout the next couple of weeks. So rather than leaving this in prime notation, I rewrote it in Leibniz notation. The reason why we're going to be using Leibniz notation is because Leibniz notation can kind of work with the laws of algebra to give us a nice, slick way to solve what's called a separable differential equation. And so by separable, what I mean is if I look at this side of the equation if I look at it as division, dy divided by dx, I can separate the dy and the dx by essentially multiplying the right side of the equation by dx. So ignore the integral symbol that's placed out in front of each side of the equation right now and just kind of think about dy being equal to what was already on the right side of the equation and then times the dx, right? One step, multiplying both sides by dx, gets me from this top line to that new line. Prior to inserting the integral symbols that you can currently see, that step is called separating the variables. If you are able to get to the point where all of the x's and the dx are on one side of the equation, and any of the y's and the dy are on the other side of the equation, that's a separable differential equation, and you can use this method to solve it. So from here, what I'm going to do is I'm going to do something that makes my differentials, the dy and the dx, go away. So if I do an antiderivative on both sides of this equation, I'm doing the one on the left with respect to y, and I'm doing the one on the right with respect to x. We'll actually look at the one on the right first because this is going to be more familiar to us. So when I do the antiderivative of 3e to the x, I can copy the 3, and then the antiderivative of e to the x is just e to the x. Power rule applied to this is going to give me x squared divided by 2. And then this is an antiderivative, so I'm going to have to add a constant over here. So you'll see I subscripted this, and we'll talk about why in about 30 seconds. I'm also applying that same process to the left side of the equal sign. So when I do the antiderivative, and there's really a 1 right here, right? If I do the antiderivative of 1 with respect to y, now I'm doing my antiderivative with respect to y. We're not that used to doing this. We've done a ton of antiderivatives with respect to x. We've done a decent amount with respect to t, but this might be the first one that we're ever seeing done with respect to y. So if I apply the power rule to this is really 1y to the 0. I would add 1 to the power, divide by the new power, so I'd get y to the first divided by 1. Like we said about the right-hand side, that was an antiderivative, so I had to insert this constant there. This is also an antiderivative, so I'm going to have to insert a constant here. Now, it's highly unlikely that the constant on the right and the constant on the left have the same value, which is really why I subscripted the one on the right a few seconds ago. From here, what we want is we want the function y that has this derivative. So I have one algebraic step to take to solve this equation for y, and that's to subtract c2 from both sides in order to isolate y. Now, when I take c1 and I subtract c2, if they're both constants, they're like terms, and I'd be able to combine them. What you see I've done is I kind of suppressed them back into a single constant c. So I'm arguing that c1 minus c2, after that's been brought to the right side of the equal sign, is just some new constant that I don't know the value of, and that's the constant that I'm renaming c. What you'll see in the next handful of videos is I'm going to begin to not put the constant on the left side of the equation, because whenever we try to isolate y, we're going to move that constant from that side over to the other side. It's going to join the other constant, and it's just going to be more efficient for us to get in the habit of just adding the constant on the right side of the equal sign whenever we solve this sort of differential equation. So this right here is actually referred to as the general solution. So let me just kind of type that in here. So this is called the general solution. We do not know what the value of c is. So that's the general solution for any function that has this derivative. What is the specific solution that has this derivative and goes through this ordered pair? So now I've begun to do some work to develop that. Can't see the ordered pair anymore. Let me scroll back up briefly. So when I put 0 in place of x, my y value that gets returned has to be 4. So what I've done is I've put 4 in place of the y, I put 0 in place of the x's, and you should hopefully be able to see what that's going to get you. E to the 0 is 1, so this piece right here is a 3. 0 squared over 2 is just 0. And then I have the plus c. So if I'm trying to solve this for that constant c, I would just have to subtract the 3 from the 4. That leaves me with a c value of 1. And then my specific solution, sometimes referred to as particular, let me see if I can include that on the screen there. So this is called the specific solution or particular solution. Depending on your professor that you have down the line, you might hear both of those. College Board is probably going to be using the term particular, if I had to guess. They have used both in the past, so you'll hear me go back and forth, use them both here and there, just so we're familiar with each of them. So general solution is the solution that we get that does not have the constant of integration solved for yet. And then the specific or particular solution is the solution that we have found the value of c for. Again, we did not call this sort of problem a differential equation when we solved it earlier in the year, but it really was a differential equation. So in the next couple of videos, we'll kind of hone in on the sorts of differential equations that we're going to begin to see. They're not all going to be quite like what we did here in number 39, or what we could have done had we discussed number 40, or even this one here that gives us a velocity function and an initial position and asks us to determine the position function. All of these are situations that are really differential equations problems that we had the capability of solving earlier in the year. In the next video, we'll see how things are going to maybe get tweaked a little bit, and we'll have to take into account a few other issues as we make our way through the next few lessons.